welcome back to the course on Foundations of Continuum Mechanics. Today we'll be talking about tensors. So tensor algebra and calculus of tensors is the language of continuum mechanics. And before we start studying a subject, we have to make sure we understand its language. So first in this course, we'll understand what tensors are and also learn about some notation so that we can start using them. So let's get into the definition of tensors. So we'll not give you a rigorous definition of tensors. Rather, what I'll do is I'll start through examples and slowly build on what tensors are. So that will be a more intuitive definition of tensors rather than giving you a proper mathematical definition, which will confuse us at this stage. So I'll say intuitive definition through examples. So let's first start with scalars. So scalars are quantities which can be described using just its magnitude. So we only need a magnitude to describe these quantities, and examples are temperature. So to describe temperature, what we need is simply a number. So for example, the temperature in this room right now is 23 degree centigrade, right? So 23 is just what we need with some units, which is not important at this stage. So distance is another example. To describe a distance, what we need is just a number. So 10 meters. 10 is just a number that we need to describe these objects. Now, we must remember that we should not confuse scalars with constants. So many a times students confuse these concepts. So constants are quantities which do not change with space or time. Okay, so let's write it down. So constants do not change with space or time. So we should not confuse constants with scalars because scalars can actually change with space and time. For example, let's take the example of temperature. So I'll denote temperature by theta. So let's write theta. So theta can be a function of x and t. So x vector denotes the position coordinate. So in this room, for example, this point in this room can be denoted by its x, y, z coordinates, which constitutes the x vector denoting its position from a defined origin in the room. So temperature usually will change with x, y, and z coordinates, that is positions in the room, as well as with time. So we'll see that temperature in the morning is much colder than what it is in the afternoon. So scalars can be functions of space and time, so they definitely are not the same as constants. In fact, quantities that change with the space and time are generally referred to as fields. So this theta, which is changing with x and t, will be known as a temperature field. Okay, so I'll underline field here because we want to stress on the fact that field is a quantity that changes with space and time. So I'll put constant in a bracket and just mention that not to be confused with scalars. Right, so now that we understand what scalars are, actually scalars are called zeroth order tensors. Right. So this gives us an understanding of what scalars are. So let's move on to tensors of higher order, and then we'll generalize the idea and understand the meaning of tensors. So next is vectors. So vectors are quantities that require a magnitude as well as a direction to describe them. So vectors are, in fact, I'll mention that first, they are first order tensors. So we are generalizing the idea. So scalars are zeroth order tensors and vectors are first order tensors, and they require a magnitude and a direction to describe them. Geometrically, we denote vectors using lines with arrows. So the length of the line will typically denote the magnitude of the vector, and the direction of the arrow denotes the direction of the vector. So for example, force. So force has a magnitude as well as a direction. So applying a force vertically is very different from applying a force horizontally on an object. So vectors are denoted using magnitude and direction, and geometrically using arrowheads. Now, vectors are mathematical objects in the sense that for any physical quantity, force for example, to be called a vector, it must satisfy certain properties of the mathematical object, that is vectors. So just let's write it down. So these properties will include the standard addition, scalar multiplication, and distributive properties that are required for a quantity to be known as a vector. This can be looked into in a mathematics book. For instance, as a consequence of these properties, we get the triangle law of vector addition. So let's quickly discuss that, because that's a very important law that helps us understand whether a quantity is a vector or not. So a very non-intuitive example of vectors is infinitesimal rotations or angular velocity. So for example, if a body is rotating, it has a certain angular velocity in the horizontal direction, and it also has a certain angular velocity in the vertical direction. So what I mean is that if the body is rotating counterclockwise like this, and then around the vertical axis it's also rotating like this. So then overall, if I look at the rotation of the body, then I'll see that the body is actually rotating at an angle which is 45 degrees to the vertical axis. So that's obtained by adding the rotations along the vertical axis and the horizontal axis. So this angular velocity actually is a vector because it satisfies all the properties that are required for a vector to satisfy. And the triangle addition law is a consequence of these properties. So in a sense, what I mean to say is that a quantity by just having a magnitude and direction may not be a vector. It has to satisfy certain mathematical properties for it to be deemed as a vector. This is a very important point because that will help us define tensorial objects. We'll discuss more on that later. So a vector V is typically denoted using three components in a three-dimensional space. So we call it Vx, Vy, and Vz. So these are the three components of the vector V in the three directions. So we'll say three components in a 3D space. So these components will change if I change my coordinate system, because depending on how I look at the world in the sense that what are my x, y, and z directions, the three components will change. But that does not mean that the vector will change. So physically, if there's a force acting on a body in this direction, if my x-axis is oriented along the force, then I only have an x component. But if my x-axis is oriented at an angle, then I get a component which is smaller than what I had earlier. But the vector, the force, does not change as such. So we must remember that the physical quantity, that is the vector, does not change, but its representation changes because we are modifying our coordinate system. So three components will definitely change, or in most cases it will change in tensorial objects if we rotate our coordinate system. So again, we'll discuss more about it when we start talking about or generalizing the concept of tensors. So now that we understand the zeroth order tensors, which is scalars, and the first order tensors, which are vectors, so let's move on to nth order tensors, and let's generalize that to completely of an nth order. So an nth order tensor requires 3 to the power of n components to describe it. Of course, in a 3D world that we're talking about, so for example, in vectors, we had 3 components. That's 3 to the power of 1. So if we have a second order tensor, then we'll have 3 to the power of 2. That will be 9 components. If we have a third order tensor, then we'll have 3 to the power of 3. That's 27 components. So remember that it's in the 3D world. So if we had a vector, which is a first order tensor, in a two-dimensional world, then we would only need 2 coordinates. So in that case, the number of components required to specify the vector in a 2D world will be 2 to the power of 1. So this 3 that we have here is because we are living in a 3D world. And in all situations that we discuss in this course later, we'll be talking about a 3-dimensional world unless I specify otherwise. Now the question occurs is that does anything which have 3 to the power of n components to describe it become a tensor? And the answer is no. For a tensorial object, or for an object to be called a tensor, it must satisfy certain properties that are required to be called a tensor. That is, again, like vectors, tensors are mathematical objects. In fact, vectors are also tensors. So for something to be called a tensor, it must satisfy the mathematical transformation property that is required for it to be called a tensor. So let's write it down. So the answer is no, as I mentioned just now. So it must satisfy certain mathematical properties and in tensors that property is called the transformation property of tensors. We will not discuss this property today. This will be discussed in a couple of lectures from today, but you must understand and remember the fact that any object which has 3 to the power of n components to describe it does not make it a tensor. So many times people confuse matrices with tensors. So matrices again are objects which have in this case if it's a 3 by 3 matrix, for example, then that has 9 components, but that does not make that matrix object a tensor. So it must, whatever is being denoted using a matrix must satisfy the tensor transformation property. Now, just as a quick peek into it, tensor transformation property basically means that if I'm looking at the object from a different orientation, so I rotate my coordinate system and look at the object again, its components will change, right? Let's just like in vectors, if I have a vector pointing this way and my x-axis also points this way, then the components of the vectors will be different if my x-axis was pointing in a certain different direction. So if I rotate my coordinate system, the components of the vector change. The components of the tensor will also change. But the mathematical rule that governs the change in the components must give you the same components that you would have got if you were actually looking at the object physically. So we will get more into this when we discuss the transformation properties in a couple of lectures from now. So we have formally written down the condition for an object to be called a tensor. So if you look at the object from a transformed coordinate system, then the new components of the object should agree with the mathematical transformation property of a second order tensor. Right? So what we notice visually when we look at the object from a different rotated coordinate system should agree if we apply the mathematical transformation property to those to that object and compare the components with the physically measured components. So now let's talk about some notation. So scalars are denoted using lowercase Greek alphabets or lowercase English alphabets. Like this. Vectors are typically denoted using an arrowhead like this, or in some cases you will see it's denoted with a bold symbol like this. A many case you'll see that vectors are denoted using its components. So the three components in the three mutually perpendicular directions will be provided rather than writing the quantity as a vector given as a bold or with an arrow. If we expand the components, component form, so that basically expands to like this. So we say that the vector is written as a linear combination of the three basis vectors E1, E2 and E3. So E1, E2 and E3 are unit vectors in the three mutually perpendicular directions. So here we'll be using a right-handed Cartesian coordinate system. So O x1, x2, x3 denotes a right-handed Cartesian coordinate system. And the unit vectors in these three directions are given as E1, E2 and E3 respectively. So in this course, as I said, we'll be using this right-handed Cartesian coordinate system. So we'll not be using the typical notation which is x, y and z directions. Rather, we'll be calling them x1, x2 and x3. So this is for the reason that it allows us to write the notations more comfortably, and as we'll discuss later today, this makes the work, or this makes the description of these quantities that are tensors very effective. So E1, E2 and E3 are unit vectors, or they're also sometimes called the basis vectors. And these basis vectors, as you may recall from the course on linear algebra, and they are orthonormal. So what that means is the three basis vectors are linearly independent, so they're orthogonal to each other. And the reason we call them normal is because they're normalized, that is, they are unit vectors. So this allows us to write every vector as a linear combination of these three basis vectors. So we'll write that down. Any vector can be written as a linear combination of E1, E2, and E3. Right. So let's move on to the notation for tensors now. So typically they'll be denoted using Greek alphabets. And so if sigma is a tensor, sometimes we say sigma ij, and we put square brackets like this. So that will mean that it is a tensor of second order. We'll also sometimes put two lines over sigma. So that will also mean it's a tensor of second order. Or sometimes, like vectors, we will make them bold. So it depends on how they're defined in the text. But in this course, we'll be using this way to denote tensors, because that not just tells us that it is a tensor, it also tells us that it is a tensor of order 2, because you have two indices, as you can see here. So I and j are called indices in this case, and this notation where you use indices to denote the tensorial quantity is called an indicial notation. Whereas the notation where you have two lines like this, or you have the quantity written in bold, is called a symbolic notation. So just like second order tensors, in fact, I'll go back to vectors. Vectors are also denoted like this, with v with an index I, and then you put square brackets around it. So that is also a method which is used to denote vectors, which are tensors of order 1. So you can see a pattern now. The number of indices that you see below the quantity written as subscript is denoting the order of the tensor. But don't take that rule strictly, because we'll soon see that the rule cannot be generalized, and it depends on the kind of index that we're dealing with. So for at this stage, you can take it as a fact that the number of indices is equal to the order of the tensor. But we'll strictly specify that rule in the next lecture. So the index I and j, the indices I and j in this case for the second order tensor can take values. So I can take values from 1 to 3. So that's the values 1 comma 2 comma 3. Similarly, the index j can take values from 1 to 3 in a 3D world, of course. I'll not repeat that again and again, because as I said that in this course, we'll be talking about the three-dimensional world unless specified otherwise. So the number of components in this sigma object that we have, the second order tensor, is going to be 3 times 3, because index I goes from 1 to 3, j goes from 1 to 3. So we have a total of 9 components. So this can be denoted in a matrix form as well. Often you will see that second order tensors are written as matrices. Now let's move on to nth order tensors. So nth order tensors typically are denoted using capital English alphabets with the indices written below it like this. And we'll see that the number of indices in this case will be equal to the order of the tensor. If you have n indices here, then we can say it's an nth order tensor, and the number of components it will have will be 3 to the power of n. And we can see that now. So each index can go or can take values from 1 to 3. So it will have a total of 3 times 3 times 3 all the way to n times. So that will be 3 to the power of n components. So if we have a third order tensor, so it will have a total of 3 to the power of 3, that will be 27 components. Right, so let's now talk about symbolic notation. So as we said that symbolic notation is where we use an arrowhead for the vector. For tensors, we'll be using 2 lines, or we use a bold symbol for both vectors and tensors. But you can see that you cannot quickly look at the object and figure out what is the order, especially in these situations. So indicial notation definitely is something which has more information in it. In fact, indicial notation is quite rich in the sense that it conveys a lot of information which the symbolic notation does not convey when you look at the equations. So we'll write a couple of merits of indicial notation. So it's rich, that is, it has more information. The algebra is much easier to do. So if you have equations with tensorial objects in an indicial notation, you can do the algebra of those tensors in a much easier way. In fact, the calculus, and we'll be discussing that in a couple of lectures from now. Calculus is also easier to do. It's in fact you can do it more rigorously, and you can present the calculus of the derivatives of the terms using indicial notation in a much better way. So it's a better presentation. And it's much rigorous. So let's go deeper into the indicial notation, because this is a notation that we'll be using in this course. So now what we'll do is we will discuss the indicial notation through lots of examples. And since we understand vectors at this stage quite well, so we will use vectors to understand and establish the indicial notation, and then we'll generalize that to second order tensors and in fact nth order tensors. So the topic, the detailed topic now is indicial notation. So vector v is written as v1 e1, where v1 is the component of the vector in the e1 direction, plus v2 e2 plus v3 e3. So e1, e2, e3 are unit vectors, as we just mentioned. So e1 is unit vector, and v1 is the component or the projection of v in e1 direction. Right, so this can be written using the summation symbol. So we can write this as summation I goes from 1 to 3 vi ei. Now when Einstein presented his 1916 general relativity paper, he was working with very long and complex tensorial equations. You may have seen in pictures of Einstein with complex equations written in the background on a blackboard. So these equations were presented in his 1916 paper on general relativity. So while uh, discussing his paper, since there were very complex equations using tensors, so he used a notation which is called the summation convention. So summation convention is, I'll briefly mention that today, and then we'll go deep into it in the next lecture. So summation convention is where this vector v, which is written as a sum going from I equal to 1 to 3 vi ei, is written simply as vi ei. So we remove the summation symbol in this case and simply write the expression. So this, the term with the red underline and the term with a blue underline, they mean exactly the same thing. So this is written under the using the summation convention. So the rule says that if an index appears exactly twice in a mathematical term, so this is a mathematical term that we have here. So this is a mathematical term. So if an index appears exactly twice in a mathematical term, then summation is implied over it. VIEI. So this is a mathematical term, and the index I appears exactly twice, then a summation is implied over it. So this is actually equal to sum I going from 1 to 3 VIEI. So Einstein popularized this notation. He did not invent it, but he popularized the notation in his relativity paper in 1916. So this notation is also sometimes known as the Einstein notation. And remember, this is a notation. You can choose not to use it. Even then, the mathematics of tensors will work. So you'll see in books, it will be written in the beginning that the Einstein notation is used in this book or in this text. So in this course, we will be using this notation. In fact, it's a very rich notation. We really want to learn it and use it to solve lots of problems in tensor algebra and tensor calculus. So in the next lecture, we'll go deep into this notation and we'll solve a few problems to understand this notation property. So I'll repeat that again next time. This brings us to the end of this lecture, and just as a quick concept check. So the first one is that vectors are tensors of order dash. So you have to fill the dash. And the second one says that the number of components of a third order tensor in a 2D world will be. So remember that we are saying it's a 2D world. And as I mentioned that the world will be 3D unless I specify otherwise. So this is that otherwise situation where we ask that the number of components of a third order tensor in a two-dimensional world will be dash. So you have to fill the dash here. Right. And as a food for thought, think about the fact that a scalar is a tensor of order 0 and a vector is a tensor of order 1. Then why do we call both of these objects as tensors? So what that basically what I'm asking here is that what is common between these two quantities for them to be both called tensors? So this is something you must think about and answer in this course. Thank you, and I'll see you in the next lecture.